Hi, my name is Aditya and I am the CEO of Automaski. Today I am going to be talking about the longest common subsequence problem, which is a foundational problem in bioinformatics to globally align sequences and to create phylogenetic trees, etc., clustering, etc. Now, I'm sure you understand what is the longest common subsequence problem, but let me try and explain it in brief. So before we go there, let's talk about the longest common substring problem. When you have when you have multiple sequences of characters like T, G, C, A, etc., found in genes, etc., or DNA, RNA, etc. Now, when you have multiple sequences, if you have to find the longest common substring across all these sequences, where a substring is basically a consecutive set of characters which are next to each other, then it is the longest common substring problem. Longest common subsequence problem is to find the common subsequence across all the sequences where the characters might not be consecutive. You have T, G, and then you skip 2, and then you have A. And this is common across all sequences. So your solution is TGA, while there is a gap between G and A. Longest common subsequence problem is NP complete and for multiple sequences of arbitrary number of sequences. Now what I'm going to show you today is solving longest common subsequence problem, and hence making a massive breakthrough in bioinformatics informatics by solving this NP hard problem in polynomial time and polynomial space. Now I'm going to demonstrate a couple of executions. In the setup here, I have a lot of FASTA files. FASTA files are basically a file format used to store one or more sequences. Now I can load up a problem with multiple FASTA files with one sequence in each file, or one FASTA file with multiple sequences defined in it, etc. Let me start showing you, and these are very well known popular FASTA files. Okay, so let me start the longest common subsequence. I'll explain what is happening. Just let it execute. Okay, let's go to the start of the problem. There are number of sequences is 4. It is printing the name of the sequence and the total number of sequence length. It has number of characters. The vocabulary is 20 and it prints the vocabulary, maximum counts and max length, etc. And then it starts the lowest common subsequence process, and then it again prints the sequences names and the lengths, and it says the maximum sequence length, the longest common subsequence is 49, and there are 3 of those sequences which you can recover, and the time it took is 15 seconds. Now I'm going to show you the Bali base MSA benchmarks. Our algorithm will rip through the benchmarks, and this is multiple longest common sequence global alignment problem. Now these are benchmark problems from Bali base. So let me run this. Okay. Let me go up. Actually, it has a lot of sequences, hundreds of them. That's why it is overflowing the buffer. Now the solution is trivial. There is maximum sequence length is only 1. and the common characters are G and L. That is what it is. Okay, but it did hundreds of sequences at one time. Let me run another benchmark. The maximum common sequence length is 4 and it is IGDL. Again, there are hundreds and hundreds of sequences. Okay, I think there are 1,000 sequences. Let me run another benchmark. This will take a long time, so I'll pause the screen. These are all standard Bali based benchmarks. The number of sequences is 136. This is a really tough problem to solve. You can actually do this and solve phylogenetic trees, etc. You can do clustering, etc. very easily. It prints the vocabulary, the max counts and the max lengths, etc. Basically the statistics involved. I'm going to pause for a while. It's done it. The maximum longest common subsequence length is 12 and it prints the sequences. The time it took is 93 seconds. Now, all of Automaski's systems are built to order and hosted in our data centers and offered to customers to be accessed remotely as a service. This is a test environment and this computer is actually hitting the test environment. And the test environment is this test environment is 1 million times slower than the production environment, and it is hundreds of times cheaper, and it can make mistakes, lots of mistakes. We are using quantum phenomena to solve these problems, and these are quantum systems, and that's all we had to show today. We have solved a NP-hard problem in polynomial time. Though a million times slower, we were able to demonstrate it on standard benchmarks. And if you have any questions, you can email info@automaski.com. Thank you.